This is section 2.1 or 2.2 continued. This time we're talking about reducing a fraction using the prime factorization method. So we're creating equivalent fractions by reducing, and we're using prime factorization that we just showed in our last lecture. Now, prime factorization method goes like this. We're going to factor the numerator and denominator into their prime factorization, or using prime factors. Then we cancel all common factors. That, remember, means to divide them out of both the numerator and the denominator, and then we rewrite the fraction. So we had just finished doing the factorization for 12 and 24 earlier, and so 12's factorization you see right in here, 2 times 2 times 3, 24 of course being 2 times 2 times 2 times 3. So we have rewriting 12 as its prime factors, 2 times 2 times 3, and 24 is 2 times 2 times 2 times 3. And then we cancel the 2's and we cancel the 3's. So one of these goes with one of these. One of these goes with one of these. This 2 is going to get left over. And then that 3 and that 3 get canceled. So one of the things that we need to remember is that when we cancel, we're dividing. When we divide any number by itself, we do get 1. And so there's a 1 left up here, and a 1 left up here, and a 1 left up here. So it's 1 times 1 times 1, which gives you a 1 in the numerator, and then a 2 in the denominator. So now we're going to do an example here where we're going to reduce 42 45ths. I've already taken the liberty of doing the prime factorization of 45 for time. So 45 was 3 times 15, 3 times 5 is 15, and 3 times 3 times 5 makes 45. You should always multiply it out for yourself. Now I wanted to do 42 with you because I wanted to point out the fact that I was finishing, just trying to say up when I ran out of time in the last lecture, is we don't have to start out with the lowest prime. So the lowest prime that goes into 42 is 2, but we don't have to start out with 2. For instance, we know that 6 times 7 is equal to 42, so we'll have a 6 and a 7. Well, 6 is not a prime number, but 7 is, so I'll circle the 7 over here, but 6 then I need to go and pay attention to. So 6 is 2 times 3. And no matter if I started out with 2 and went through it as the factors of 2 times 21 and then breaking down 21 into 3 times 7, I always get the same prime factorization. It won't matter. So I'll rewrite the prime factorization here as 2 times 3 times 7. And now I'm going to go ahead and I'm going to reduce 42 45ths by using the prime factorization method. So the numerator 42, I'm going to write that as 2 times 3 times 7, our prime factors. And then in the denominator, I write 3 times 3 times 5, its prime factors. Now I'm going to cancel. A 2 in the numerator, there's nothing to cancel here, so I skip over it. One of these 3 goes with one of these 3. When I cancel, I am left over with 1. No more 3's to cancel, and 7's, no canceling down here, so I don't have anything to do. And now I can just multiply out. So I'm going to say that this is equal to 2 times 1 times 7, which is 14. And then in the denominator, 3 times 5, which is 15. And if you'll remember right, that was the exact same answer that we got in reducing this using the GCF method. Both the GCF method and the prime factorization method, there's no difference in reducing these things. Oops, I think I skipped it. I wanted to show you that it was exactly the same. And I guess I erased it. So there we are. It is 14/15. So we have the exact same answer no matter which way we do it. The prime factorization method, our benefits here is that we are going to use this exact same method when it comes to the end of our semester, using this to reduce rational expressions, which are icky looking fractions. They're messy fractions, but we'll use this same thing. Next, we're going to discuss the fundamental theorem or principle of fractions, usually the fundamental theorem, and see how we've been using that all along. So we'll return with that.